All right, let's go ahead and start just by talking about what a limit is, just intuitively. We'll get into like maybe a bit more formal of a definition later. But right now you can think of a limit as just like where does the function go? And I think pictures are really helpful, so I'm going to draw one. Oh, I need to open one up. There we go. So let's say we have our coordinate plane right there, and then we have some kind of function on it with a hole in it right there. Fairly simple. But if we're looking, we can call this point C, and this will just be, we'll call that 1, because 1 is an easy number. Okay, now if we are looking for the limit notation, if this is function f of x, we'll start by writing it formally. The limit as x approaches the value of c of our function f of x. And that is how we would read this whole statement. The limit as x approaches c of f of x. And to answer this question, we can just ask ourselves, where does the function go? And you can almost imagine it like two people running from opposite ends of your function. So one person runs from this end, another person runs from this end, and you think, where do they meet? And they will, of course, meet up right at this spot right here. Now, technically, they can't ever step on that spot if they're running, but they could like reach across and give each other a high five. Basically, they're close enough to touch each other. So when they can give each other a high five, or in this analogy we're using, we can say that the limit does exist. So we would say the limit is equal to the value at this point, which is 1. Does that kind of process make sense? So fairly straightforward. If instead we had a graph that looks something like this, well, in our analogy, if we had two people running, one going from this direction and one going from this direction, well, there's no way that they could reach across and give each other a high five. They're just too far apart. So in this case, we would say that the limit as x goes to c of whatever our function is does not exist, or d(n)e). Easy enough, right? Okay. Cool. Now, if you'll give me one moment, I'm actually going to open up something that I went ahead and prepared. I forgot to log into earlier, so 1 second. Okay. All right. Now I'm going to share this for anyone who may be watching the recorded version. And there we go. So let's just take a look at some of these graphs. You're not sharing your screen. Right. Thank you. So taking a look at some of these graphs, first off we have x squared minus 9 divided by x minus 3. Now, I'm interested in specifically the limit as x approaches positive 3. Now, just looking at this graph, what could you tell me that limit is? At positive 3, let's see, we would look at, here's x is positive 3, right? You can see my mouse, right? There it is. So then we trace it up and say, well, from the left, it looks like it approaches which value?
Sorry, is that a 6?
Yeah, sorry. Okay, yeah. Sorry, yeah. That is a 6. And from the right, it looks like it is also approaching which value? Right, the 6 as well. If we actually look at it, we can see that 3 is actually undefined. And the reason being, if we actually look at our original function, when we plug in x is equal to 3, on the denominator we have 3 3 minus 3, which gives us 0, and we can't divide by 0. But just by looking at the graph, we can see that the value from the left is the same as the value from the right, and it's 6, so we can say that the limit as x approaches 3 is 6. Let's take a look at another one. Here we have x squared plus 1. What is the limit as x approaches 2?
5.
Right, it is 5. In this case, from the left, we have 5 right here. It's about 5. And from the right, here we have 5 as well. In fact, this one, the limit is exactly the same as the function value. That's also allowed. Limits are often helpful when we have discontinuities, like in the first one. But that doesn't necessarily mean that the limit can't also be applied to functions that do have that are just continuous everywhere. Make sense? Okay. Go and look at the third one. This one's a really common function, the rational function 1 over x. Now I am interested in the limit as x approaches 0. Any thoughts on this one? It's a bit trickier.
Infinity, but it depends on from which side you're coming.
Okay, so you say it depends on which side you're coming from. What if I'm not asking about from which side? I'm just asking about the limit.
It doesn't exist.
Right, it doesn't exist because it goes off in completely different directions where people can never give each other a high five. They're sad it doesn't exist. If you're looking at x approaching from the left, from the negative side, what would that be? Right, negative infinity. Perfect. All right, what about 1 over x squared as x approaches 0?
Positive infinity.
Right, positive infinity, because both from the left and from the right, it goes up towards infinity. There is technically some I don't really want to say disagreement, but it doesn't exist. In my opinion, both are technically correct, but
It depends like where you are.
yeah, it doesn't depend on like where you are on the function. It really just depends on who your professor is, honestly. But yes, that might be something you would want to double check with your professor, whether they want you to say this is infinity or it doesn't exist. Okay. Oops. All right, now let's look at a weirder looking function. This is a piecewise function. I am interested in the limit as x approaches 0 once again.
Does not exist.
Right. It also does not exist. What about the limit from the negative side?
2.
Right, and from the positive side?
1.
Right. And this is actually one thing that we can actually use to determine if a limit exists. We can say, well, if the limit from the left is exactly equal to the limit from the right, then the limit exists. That's a more formal way of saying like a limit definition. All right, but yes, this limit does not exist. And one more. I'm interested in the limit as x approaches positive 1. From just the limit as x approaches positive 1.
Negative infinity.
Okay, you say negative infinity. Can I get you to elaborate?
I just like literally the whole bottom of the graph is going to approach -1, and that's too many numbers, so I just think it's negative infinity.
Right. So you think it's negative infinity because you say the whole bottom of the graph.
Is because we're approaching x equals 1,
Mhm.
right?
What if I'm approaching x equals 1 from the negative side?
Does not exist.
Right, so is does not exist the same thing as negative infinity?
No.
No, so does our limit exist?
No.
Right, our limit actually doesn't exist. In this case, it's because on one side, we really have no function, right? The function just isn't defined there. So when we try and take the limit where the function isn't defined at all, there's like no function we can approach along. So we have to say that from the negative side, the limit doesn't exist. From the right-hand side, you're exactly right. We can say that the limit would be negative infinity because if we trace along our curve from the positive side, we do get closer and closer to negative infinity. But because we can't even trace the curve on the left-hand side, it has to be does not exist.
So if we specified which side, we could give a limit, but because we didn't specify, it just does not exist.
Right, that is exactly right. If I specified from the positive side, you would be able to say negative infinity. If I specified from the negative side, you would still have to say does not exist. That all makes sense? Ooh, cool. All right, I will go back to sharing OneNote. There we go. Perfect, perfect. So that's basically getting limits from a graph. Not too difficult. You basically just look at the graph and say, where does it go? There are some other methods we can use to evaluate the limit, though. Let's take a look at what is called the tabular method. Okay. And the whole reasoning behind this tabular method is basically, what if we just check closer and closer values to our limit point? So I'm just going to write that down. Check closer and closer values to the limit point. Okay, so I think this one is best illustrated by an example. So we're actually going to start with an example. And this one is a very classic limit. The limit as x approaches 0 of sine of x divided by x. And basically with the tabular method, all we're doing is we're checking for a given x value, we want to know what our function value is. So we're interested in the limit as x goes to 0. So I'm going to say, let's check -1, -0.1, -0.01. And also I want to check from the right-hand side as well, because we need to make sure that they match. They approach the same value. So I'm going to check 0.01, 0.1, and 1 as well. And as you can see from the left-hand side, we're getting closer and closer values to what's actually 0. We don't necessarily know the value at here, but we can estimate it based on these closer and closer values. So plugging -1 into sine of x divided by x, you get 0.841. I know because I did this beforehand. For -0.1, you get 0.998. And then for -0.01, you get 0.99998. And from the positive side, at 1 you get 0.841. For 0.1 you get 0.998. And for 0.01, you can get 0.99998. All right, so what value do these approach?
1.
Right, 1. So what is our limit?
1.
Perfect. Not too bad, huh? Any questions about the tabular method?
No questions about the method per se. I was doing a problem on my homework and I couldn't guess the value of the limit.
Mm-hmm.
Because it wasn't as clear as this. Here you can see both of them getting smaller, but on my problem it wasn't going anywhere specific. I don't see so.
Right. In some cases, it might not be as clear as this. This is a very clear example.
Yeah.
In the cases when it's not quite as clear, you may want to, there's really one question you need to ask, and that is, does it at least look like they're going towards the same value, even if I don't know quite what that value is? If it looks like they're going towards different values, then your limit doesn't exist, right? Because the left side isn't the same as the right side. If it looks like they are going towards the same value, you just don't quite know what that value is, really you just have to give your best estimate. The tabular method usually isn't exact. It's basically just there to give you an estimate. So a lot of it also just depends on how close are the values that you choose for here and here. If you choose more precise values, you'll get a more precise answer. If you choose less precise values, you won't get as precise of an answer.
After you give all the methods, like, will you say like what type of method goes to what type of problem? Because I'm guessing you can't do this method with like every type of problem.
I mean, theoretically you could. My main drawback with this method is that how do you take the sign of 0.01? You need to use a calculator for that, right? So for this method, you basically need to have a calculator, and I just usually don't have one on me. Otherwise, if you can imagine the graph, you can solve it graphically. But for me, what I usually actually end up doing is trying to simplify it, seeing what I can cancel, stuff like that. But really, whichever method you think works best for you is the best method to solve the limits. There's no really right way to solve every limit problem. There are probably some ways that work better than others. But as to like just deciding which one to use,
They all work the same.
they'll basically all give you the same answer.
I have found that like you don't have to know what all the graphs are, but it really, really helps.
Yes, it definitely does help to know your basic graphs.
Yeah.
Just like the general shape, and then at least know like a little bit of how some transformations work. So like knowing that, hey, if I add 3 at the end, it's going to shift up 3, stuff like that. Just because a lot of the times a graph is the first look you can get at a problem, and it's really easy to just look at the problem and see, okay, this is the general shape of it. But yeah, definitely helpful. Let me check in with anyone online. Nope, still no one. That's okay. Let's see. Do you happen to have a calculator on you?
Yeah.
All right. I'm actually going to give you a tabular method problem.
Yeah.
I'm still on. Okay, there we go. Practice. Go ahead and try and figure out the limit as x approaches 0, this time of 1 minus cosine of x divided by x. And usually you will be given intervals for your table, so I'll go ahead and give you those as well. They're basically just going to be the same as the last one. All right, so go ahead and you can just call out answers as you get them.
-1 is -0.45 or 46.
Perfect. That's good enough.
The next one is -0.05. I don't know how many decimals.
However many you think is important. guess the deciding factor for the number of decimals you feel like you need to go to is how many do you need to see what your limit is?
Next one is -0.005.
Okay. What about from the right-hand side? The positive side.
Oh, I don't think I did that right. I got 99. 1 moment.
Maybe not.
Okay, 0.005.
And that was for which value?
0.01.
Okay. Perfect.
And I mean, if we're following the trend here, the next one would be positive 0.05
You are correct about that.
and positive 0.46.
Yes, yes. That is in fact correct. So what is our limit?
0.
Right. So fairly straightforward. Yep. Let's see. So these two limits that I actually showed in the tabular method are two limits you should probably memorize just because it's easier to memorize them and they come up a lot. I'll go ahead and write them down again. Limit as x approaches 0 of sine of x divided by x is equal to 1. And also the limit as x goes to 0 of 1 minus cosine of x divided by x is equal to 0. These are very helpful limits to know, so it might be best just to memorize them or take note of them so when you see them you can be like, those are special. All right, but are we good for the tabular method?
Let me write this down.
All right. So next we'll talk about one-sided limits just a bit, although it seems like you seem to know mostly what these are already. Oops, that's not what I want,
That's what I've spent all morning doing.
right? All right, well, it never hurt to brush up a bit more, huh? So again, this is the same kind of question we need to ask ourselves as when we're looking at just like a normal limit. Where does it go? Except this time we only have one person running along the function. So where does it go? But this time we need to add on when looking at only one side. And I'll underline all of those just for fun. Okay, so we'll start with an example. And this example is going to be a piecewise function because I like piecewise functions. So we'll say our function is defined pretty simply. It's going to be 0 for negative x values, and it's going to be 1 whenever x is positive or equal to 0. Well then, if I'm approaching 0, which we know there's a jump discontinuity at 0. If I wanted to sketch my function, it would look something like this. I'm going to draw it in red so it's easy to see. With a hole right there, filled a circle, just like that. That's what our function looks like. So if we're approaching 0 from the negative side, we can think about tracing just along this side. And at 0, well, our function approaches which value?
0.
Exactly right. It approaches 0 because we're only looking at the left-hand side. It's almost like we could completely cover up the right-hand side and just ignore it. All right, but what if instead of approaching from the left, we approach from the right-hand side, the positive side?
1.
Right, it approaches 1. And again, fairly straightforward. We could even look at it without even paying attention to our graph. We say, well, when we're approaching 0 from the positive side, we only care about this portion of our piecewise function. And when we're approaching from the negative side, then we would only care about this part. Okay. Oops. All right. Now the question is, what if I don't take a one-sided limit? What if I just ask, what's the limit as x approaches 0?
Does not exist.
Right, it does not exist. And this, again, goes back to what I mentioned earlier. If the limit as x approaches a point from the negative side does not equal the limit as x approaches the same point from the positive side, then we can say that the limit as x approaches that point does not exist. Well, cool. All right, let's go ahead and do a couple of practice problems. Sound good? Let's see how we're doing. 2:30? Yeah, we're fine.
What time does
You have somewhere you need to be?
no.
Okay, then technically we can go until 3:30.
Fun?
Although that's a bit long, so I usually try and keep it just a hair shorter. But of course I can answer any questions you might have. All right, practice. Practice problems. We'll start with, again, something fairly simple. The limit as x approaches 0 of 1 over x. Except this time we're not going to be using any kinds of graphs. 0 from the negative side, I mean to add. You're welcome to draw your own graph if you want, but it is not necessary.
These are infinite limits.
Some of them are.
That 1 over x was like the bane of my existence today. So am I supposed to solve these using the tabular method?
Using whichever method you want.
So today I was doing the like number line where I plug in 1 before and 1 after.
Mm-hmm. That is basically the tabular method. Some of these, I guess my question is, do you know what the graph of 1 over x looks like?
I do now.
All right.
After this morning.
So I will say that for these first 3, the way I would approach it is by just sketching myself a graph and looking.
So you would just sketch the graph.
Uh-huh.
So like the fraction ones, like I did a number line for the top and the bottom, and then just decided from there.
Okay.
But with the graph, as it's approaching 0 from the negative side, it's gonna go to negative infinity.
Mm-hmm. That was weird looking negative. Okay. Okay. There we go.
And from the positive side, it's positive infinity.
Yep.
And ln was something like that, I think.
Like what? Sorry. I think you were right. I just maybe only talked about the corner mile.
Yeah, like it was going something like that, but from 0 from.
So you're saying something like this?
Yes.
Right, right.
So from 0 to positive, it'd be negative infinity.
Right. You look along this way and it approaches negative infinity. So those three were all really easily solved just graphically.
Yeah.
I noticed you didn't even draw out a graph. So these three, perfect, graphically solution. Yeah. Yay. Same and same. Perfect. All right, this fourth one is a bit different, huh?
Yeah, so that's the type of one that I would do the little number line thing. Tabular method.
You could. I will say, though, that there is an easier method.
I would like to learn that easier method, please.
Okay. So let's actually start by looking at the denominator.
You can't plug in 0 because it equals 0.
Right. If we plugged in, or I guess if we plugged in our value 2,
yeah.
Well, then we would have 0 divided by 0, and that's not allowed. But is there a way we can factor the denominator?
X plus 2 and x minus 2.
Exactly right, x plus 2 and x minus 2. So then if we rewrote this, can we cancel anything?
Yeah, the x minus 2's, so it'd just be 1 over x plus 2.
Right, right. So then we can say that the limit would be the same. And what is the limit as x approaches 2 from the positive side of 1 over x plus 2?
Do we plug it in?
Well, does it work? Do we get a real number if we just plug it in?
Yes, 1 over 4.
Yep. So that is actually one of the first things you should do when you're looking at a limit. Just plug in your number. If you get a real number, cool, you're good. That doesn't necessarily apply for piecewise functions.
Yeah.
But for all these over here, it works. These three, of course, I guess on all of them, you wouldn't necessarily get a real number. But if you simplify and get a real number, that is your limit. So that is the way that we solve problem 4. Perfect, perfect. Now, 5 and 6 are maybe a bit different. It's the same function, just from the left and then from the right.
Okay, so if we're looking at it coming from the negative side, we would look at the top one.
Mm-hmm.
So just, I
Right.
haven't looked at these types yet.
Well, your reasoning is actually correct. You said we're looking at the top. If we're coming from the negative, we only care about the top function. So just.
Yeah, but it's just x.
Just the x, right?
So it'd just be 2.
Right. Then we would just ask, well, what's the limit as x approaches 2 from the negative side of x? And well, that's really easy. 2.
Okay.
All right. What about the second one?
Coming from the positive side, it'd be the bottom function. And so you just plug it in 2 to the, is that cubed?
Yep, yep.
Is 8 times 4, 32?
Exactly right.
That's easy.
Yep, yep. So then if I asked, well, what's just the limit as x approaches 2 for that same function, x, 4x cubed?
It'd be 32.
Well, from which side? I'm not asking about a side. I'm just asking as x approaches 2.
Right, but the bottom function is bigger than or equal to, so you would use the bottom function, and wouldn't it equal 32 again?
Right. If you're just looking at the value of 2, at f, you're answering the question, what is f of 2?
Oh, okay.
Yeah.
So it does not exist.
Right, because the limit from the left-hand side right here
That's different.
is different from the limits from the right-hand side. So we would say this limit does not exist. And this is something that trips up a lot of people when looking at piecewise functions, because they say, well, basically exactly what you said. They say, hey, this is bigger than or equal to, I can just plug in 2. But that's not necessarily true. You would need to check the limit from the negative side and from the positive side. And in this case, because they're different, we have to say it doesn't exist. All that makes sense? Cool, cool. All right, just check up. Cool, cool. No one showed up. Fair enough. So next up, let's talk about some limit laws.
They look like log rules to me.
They do. That's because they are kind of similar, honestly. Yeah, a lot of things in math end up just being kind of similar, which is kind of convenient, honestly. Yeah. They're a bit different from log rules, though. Log rules have slightly weirder properties. So let's say we have 2 limits. The limit as x approaches point A. So we have 2 functions, f of x and g of x, and the limit as f of x approaches a is L, the limit as g of x approaches a is M. Well, first off, we have our addition rule. We can say first off that the limit as x approaches a of the sum of these functions, f of x plus g of x, well then this would equal L plus M. The limit as f of x approaches a plus the limit as g of x approaches a. Similarly, we have our subtraction rule, which is basically just the addition rule, but with subtraction instead. But I'll go ahead and write it out explicitly. This time, instead of the sum, we just use the difference, and that would be L minus M instead of L plus M. Now we have our multiplication by a constant rule, where if C is some kind of constant, well, then we can just multiply our limit by it as well. We also have product rule, where instead of multiplying by a limit, we multiply by the other function. And one more, basically related to the multiplication rule, we have the division rule. F of x divided by g of x this time. And this one would be exactly what you expect, L over M. And this is, of course, assuming that M is not equal to 0. Because if M is equal to 0, well, then we run into problems because we can't divide by 0. But yeah, that is basically it for our limit laws. They're fairly straightforward, pretty much what you expect. But we'll do some practice problems with them anyway. We'll start with one example though. So let's say we have limit as x approaches to f of x equals to 3. The limit as x approaches to g of x equal to -1. The limit as x approaches to 2 of h of x equals to 0. And the limit as x approaches 3 of k of x equals to -4. Well, for our example problem, we'll say what is the limit when, or I guess all of these questions are going to be what is the limit of, this one will say f of x minus 4 times g of x. Well, by my subtraction rule, I know that this should be equal to whatever f of x is, the limit as x approaches to f of x, so 3, minus, by my multiplication rule, I know I can just multiply my limit for g by 4. So 4 times the limit of g. So 3 minus 4 times negative 1 gives me positive 7. Straightforward enough? Cool. Time to throw some practice problems at you. Again, we have the limit as x approaches to 2 of 2 root f of x. See, already making things a bit more complicated. And we have g of x squared. All right. Practice problems for you.
E is 6.
You're saying is 6. Can you explain why?
2 times, oh, I forgot about the square root.
Well, how do you think you'll deal with the square root?
I gotta multiply, but then I gotta multiply the whole thing. I mean, not multiply square.
Oh, you could. That would definitely work. So,
Would you do it a different way?
I mean, technically it doesn't really matter if you square it first or if you just take the square root. I think what you're thinking of doing is actually a really smart way to use your multiplication rules more like your limit laws more like they're laid out. And I think what you're saying is just take this whole limit statement and then just square it, right? And that would definitely work. But the easier way is just to say 2, what is the square root of 3? And then multiply by
-1 squared, which is just
1. Yes.
Oh, okay. So you don't even have to like take it off or anything.
Nope.
Let it be.
You can just let it be.
Okay, the next one I think is 0.
Why do you think it's 0?
F of x is 3 times -1, -3. H of x is 0, so you can't divide by 0, so it's just 0.
Well, if we can't divide by 0,
This does not exist.
right. We could also say it's undefined. All right, what about for D?
I got 9. It was -1 plus 4, which is 3. H of x is 0 plus 3, so that's 3 times 3 plus 9.
Okay. You would be correct if I hadn't made this a trick question. sorry.
Okay.
So I have a question. We're approaching x is equal to 2 here, right?
Mhm.
Well, do we know the limit as k approaches 2?
No.
We know the limit as k approaches 3. And so if we don't know the limit as k approaches 2, we can't really know this. So that is one thing that you should just keep in the back of your mind. In order to use your limit laws, they need to be approaching the same values. Bit of a trick question there. Sorry for pulling it on you. I just wanted to emphasize that point.
I mean, you did. Okay. And that's all I worked through in my head. So g of x is -1 minus 3, which is -4. And then h of x is 0 plus 3, which is 3. -4 times 3 is 12, -12.
Perfect.
And then f of x is 3. 3 squared is 9. 9 times 3, 27, minus g of x, which is -1.
Final answer.
Minus -1, so that's +1, so 28.
Perfect. All right. Yep, so that's the limit laws in action. Key takeaways, make sure you're not dividing by 0, of course. Watch out for trick questions. Make sure you can apply your limit laws before you do. Yep. But other than that, pretty straightforward. Any questions? Cool. All right. So we'll move on to the last topic, which I believe you should have covered in class, Squeeze Theorem. Is that familiar at all?
I'm sure the class covered it.
Okay.
However.
All right, well, we will write it, we'll go over it. Squeeze Theorem.
I remember her writing that down.
Cool. So Squeeze Theorem is, it's useful. There are definitely certain situations where it's more useful, but I guess we'll just start with some kind of intuition. Kind of weird question. Have you seen Star Wars: A New Hope? No? All right, we'll skip that analogy then. We'll go to a different analogy. So let's say a person is walking in a canyon. Here's the wall. Oh, here's the walls. And the person is just walking along in the canyon happily on a nice hike. Well, as they walk along, let's say that the canyon walls get narrower and narrower. Well, we can't say exactly where they are height-wise, right? Vertically up or down within the canyon. But we do know that wherever they are, they have to be between the walls, right? Because they have to stay in the canyon. They can't just climb out.
Right.
So then the closer the canyon walls are, the more we know about their position, right? Well, that's kind of the intuition behind Squeeze Theorem. What if instead of this top function and this bottom function being canyon wall, or this top and this bottom being canyon walls, we call them one function and another function. And instead of a person in the middle, we had a whole new function entirely. We'll draw this other one in red, because why not? Well then, the closer the top and bottom functions are, the more we know about the value of the middle function, right? So that's kind of the intuition behind Squeeze Theorem. Let's actually define that mathematically now. And it's going to be a wee bit boring, but just let me know if you have any questions about it, okay? So basically, we need to say we have three functions, and one of them, in this case g of x, is always between the other two, right? Just like we have in our example with the kingdom. Well, if we know this, then we have to say that the limit as x approaches some point for those very same functions also has to follow the same rule. Make sense? So we can say if this, then this. Yep. And that's basically the whole definition. So let's see how this is actually useful. We'll take the limit as x approaches 0 of, again, this is another pretty classic example, x sine of 1 over x. Right? Well, here's the thing. I know that sine of x, or sine of anything really, so sine of 1 over x, because sine is at most 1 and at least negative 1, or at most 1, but definitely bigger than negative 1, I can write that it's always bigger than negative 1 and always less than positive 1. Right? Well then, if I put an x in there, then I get that negative x is always less than or equal to x sine of 1 over x, which is always less than or equal to positive x, right? Did you follow with that step?
You just multiplied everything by x.
Right, right. Because I'm trying to get this middle portion, which is complicated, to look like my original function. But then x and negative x aren't complicated at all, right? So by the squeeze theorem, because this statement here is true, I know that their limits should also follow that same rule. Oh, I forgot my mistake for that one. All right, so let's solve the outside limits. What's the limit as x approaches 0 of just negative x?
0.
Right, 0. Pretty easy. What about for the right-hand side? The limit as x approaches 0 of positive x?
0.
Also 0. So what does that tell us about the middle value?
It has to be 0.
It has to be 0. So what's our limit?
0.
That's how the squeeze theorem works. Pretty neat, huh? You still look
This
at
is
this?
really like simplified. I'm like.
I did use a. I used a classic example. I will throw in some practice problems that we'll go over that will be a bit more complicated.
Yeah.
I'm
like, this looks easy now, but like he's ready to.
Yes. But you'll notice that in this problem we did have trig functions. We had sine, we had not cosine, but we did have sine. And that's really where squeeze theorem is particularly useful. I find that I use squeeze theorem the most for trig. Because it's really easy with sine and cosine especially to set up this equality, this inequality. The negative 1 is less than or equal to sine, which is in turn less than or equal to positive 1. Yep, yep. Ready for some practice problems?
Yes. I am quickly just looking through my homework because I know there was one limit problem where I had two different peer tutors down there who just couldn't explain it to me, and it had to do with cotangent. They were like, units, I don't know.
Okay.
So I'm like, is this what I was supposed to do, the squeeze theorem?
Maybe. I can take a look at it in a second.
Yeah, go ahead and do your problems.
Let's just go over practice problems and then we'll just
Yeah.
call it good, since this is really the last little bit. Practice. The limit as x goes to 0 of sine of x cosine of 1 over x squared. Limit of x goes to 1 of f of x, where in this case I'm giving you inequality. And this one I would say is actually easier than the first. So you may want to try this one before you try the first one. And we'll go with one more.
So do I just work it out with you?
You can work it out on your own. You can work it out by talking it out with me, however you want to do it.
3x minus 2. So I just plug in the number, right?
Yep.
So 3 minus 2 is 1. And then x cubed would still be 1. So the limit of that has to be 1.
Mm-hmm. Perfect, perfect.
The second one. So is it like sine of x is less than or equal to f of x?
For part
Like,
A, I
the
guess.
second one was set up like the one that we did before.
Right, right. If we're looking at part A,
So how do we set that up?
what's your most complicated part?
All of it?
Good answer.
Or is all of it what goes in the middle?
That would be a little too much, because then we wouldn't necessarily be able to make it perfectly tight, right? Let's try and, if you were to cut this whole thing right in half, where would you cut it?
Sine x and then cosine 1 over x squared. I'm
Right.
guessing the cosine one is the harder one.
Right. Especially because we can plug 0 into sine, right? Can we plug 0 into cosine of 1 over x squared? Right. That's going to give us a problem. So let's try and write an inequality to get rid of that cosine of 1 over x squared.
Inequality.
What is cosine always bigger than?
Bigger than negative 1.
Exactly right. And what's it always smaller than?
1.
Perfect, perfect. So there we have an inequality. How can we turn it into this one right here?
How can we turn the whole inequality into sine over x? Or sine of x?
Into sine of x times cosine of 1 over x squared.
Oh, multiply everything by sine x.
Perfect, perfect.
So negative sine x.
Good, good. Now what?
Okay, and now I forgot.
Okay, don't worry. Let's try and write it with the limit statements. How about that?
So now we plug in.
Mm-hmm.
Okay, so negative sign of 0. One.
What's the sign of 0?
Is this part of the circle thingy?
It is part of the unit circle. So here's our unit circle. Our sign is our y value, right?
So 0.
0, right? And then make it negative. Doesn't matter since it's 0.
Okay, and then sign of 0 is still going to be 0. So the middle has to be 0.
Mm-hmm. So our answer would then be 0. Make sense?
That's a lot harder.
It wasn't
looks a lot
harder.
harder than it should have been.
Yeah. Yep. So I guess just in general, it can be helpful to start by saying, what's the most complicated part? And see if you can simplify that complicated bit down. So in this case, cosine of 1 over x squared is hard to deal with. So we just try and avoid dealing with it at all by just using the squeeze theorem.
Okay. So the bottom would probably be the same thing. So first we would do like 1 minus cosine squared pi over x would be what goes in the middle.
Perfect, perfect. Oh, that's not what I want. Right? Yep, but that is exactly right. You said 1 minus cosine squared of pi over x goes in the middle. What goes on the outside?
Is it still the highest cosine can go as 1? So would it be 1 minus 1? Or would everything still just be 1?
Well, you are thinking correctly. We just need to maybe extend that a bit further. So you're saying the biggest cosine can be is positive 1, right?
Then
So the biggest cosine squared can be is
1.
also 1, right? So then 1 minus 1, or in other words, the biggest amount we could take away would give us the minimum value of 0,
Okay.
right? Because there's no way we can possibly be subtracting more than 1.
Mm-hmm.
So 0 is actually going to be our lower bound,
Oh, okay.
because there's no way we can subtract more.
Right. Okay.
Now, what's the least amount we can subtract from 1?
Still 1?
Not necessarily.
0?
You say 0, good. Why do you say 0?
Because that's the least you can or like, I'm not sure.
All right. Well, your intuition is correct, so that's good. A number squared, can that ever be negative?
Yes.
We take a number and we square it,
I mean,
well, then it's always going to be positive, right? Because the
Right.
negative is going to cancel.
Yeah.
So 0 is the smallest number we could possibly subtract, because there's no possible way we can get a negative by squaring something, right? And we also know that cosine can give us 0.
Cosine can't give us 0?
It can.
It can.
It can. Right?
But it can't give us a negative.
Uh,
We're not squaring it. Can't give
right.
us.
Squaring can't give us a negative number. But remember, if we're looking at our unit circle, it's the x value. So here we could see this is a value that would give us a cosine of 0. That's pi over 2 right there. But here's our inequality that we've set up. Right? Do you understand how we got to here?
Yes.
Okay, okay.
Theoretically.
Right. So how can I turn this middle portion into this?
Multiply by x squared, so x squared times 0 is still 0.
Mhm.
And then x squared times 1 minus cosine squared pi over And then x squared.
Perfect, perfect. And we're looking for the limit as x goes to 0, right?
Mm-hmm.
So then if we write that in,
So 0 is still going to give 0.
right?
And if you plug in 0 for x squared, it's still going to be 0. So the middle has to be 0.
Exactly right.
There has to be problems where these won't give us the same number on both sides, right?
Yes, there are definitely problems when you won't necessarily get the same number on both sides. So then in those cases, like what if instead on this right-hand side, ignoring what we actually put down there, but what if instead we had 1? Well, then could you say a precise value for the limit?
No, would it just be 0 to 1?
It would have to be somewhere between 0 and 1. But you couldn't say exactly what it is.
So like the answer would it just be that and just put x in the middle?
Well, the answer, I guess this wouldn't be an answer. You would need to figure out a different way to solve it. You could either come up with a better limit so that you do get the same number on the left hand and right hand side, or you could use a different way to solve it other than just squeeze theorem.
Okay, so squeeze theorem is going to be for when they match on both sides?
Right. Only if the left hand matches the right hand can you say you get a perfectly tight limit and say exactly what your value is. Of course, like if a question is specifically asking for like a range, then it might be fine. Because if you find a range of 0 to 1, then, but otherwise, you would want to look specifically for this side being equal to this side. Make sense?
Yeah.
I'm actually going to stop recording.